Morning students. So today class continues with the problems. In the last class we ended with the problems on microscope. So today we solve few problems on telescope. So in the first question, a small telescope has an objective lens of focal length, objective lens of focal length 140 centimeter and an eyepiece of focal length and eyepiece of focal length 5 centimeter. What is the magnifying power of magnifying power of the telescope? Magnifying power of the telescope for viewing distant objects. For viewing distant objects when first one, the telescope is in normal adjustment. Telescope is in normal adjustment. So this one is the first one, when the telescope is in normal adjustment. And second one, the final image is formed. The final image is formed at the least distance. At the least distance of distinct vision. That is 25 centimeter. So least distance of distinct vision is 25 centimeter. So in the problem, they are considering one small telescope. They given the objective lens is 140 centimeter and the eyepiece lens is 5 centimeter. In telescope, the focal length of the objective lens is greater than the focal length of the eyepiece. So here we have to calculate the magnifying power, that is M. For the two cases, the first case is for normal adjustment, that is image is formed at infinity. So magnifying power we have to calculate when the image is formed at infinity, and the second case is when the image is formed at the least distance of distinct vision, that is the image is formed at 25 centimeter, that is the least distance of distinct vision. So here if you write, so the given is f of objective lens is 140 centimeter and f of eyepiece is 5 centimeter. Here we have to calculate the magnifying power at infinity and magnifying power at least distance of distinct vision. So we know for first case we know the magnifying power M is equals to F0 divided by Fe. So magnifying power is equals to focal length of the objective lens to the focal length of the eyepiece. So we have f4 value is 140 centimeter, 140 divided by the eyepiece length is 5 centimeter, then 5 2s are 10, that is m is equals to next 5 8s are 40, that is m is equal. So magnifying power has no unit, that is m is equals to 28 when the image is formed at infinity. The magnifying power m is equals to f4 divided by fe, that is equals to 140 divided by 5, we get m is equals to 28. So next, second case, when the image is formed at least distance of distinct vision, that is m is equals to, we have the formula, that is m is equals to f4 divided by fe, f4 divided by fe into 1 plus, that is the least distance of distinct vision. We have the least, this one is for the, if we didn't consider this one, it becomes only for the image is formed at infinity. For the least distance of distinct vision, we have m is equals to f4 divided by fe into 1 plus fe divided by d. So this is the formula for least distance of distinct vision. Now we have to substitute the values. That is m is equals to, here f naught by fe, that is 140 divided by 5 into 1 plus 5 divided by the least distance of distinct vision, that is d, the given, that is 25. So 5 ones are 5, 5 are into, it becomes, here it is 28, 140 divided by 5 into, here LCM becomes 5, 5 plus 1 6, 6 divided by 5. So here we simplify 5, 5 is 25, remaining is 3, 5.6. That is 5.6 into 6, 6 is 36, 6 5 is 30, that is 33.6. That is m at least distance of distinct vision, right? So you have to remember these formulas, that is m is equals to f naught by fe. This one is for the image is formed at infinity, and here one more term will be added here, 1 plus fe divided by d. So this one is the magnifying power for the image is formed at least distance of distinct vision. So m is equals to 28 and m is equals to 33.6, right? For the same question, if you find few more parameters for this question, here one more, for the same question we have few more sub questions to find what is the separation in that first one. What is the separation? What is the separation between the objective lens and the eyepiece? Between the objective lens and eyepiece. And the second one, if the telescope is used to, if the telescope is used to see the object, if the telescope is used to see the object, to see used to view a 100-meter tall tower, 100-meter tall tower, 3 kilometers away, 3 kilometers away. What is the height of the image? What is the height of the image? What is the height of the image of the tower? Of the tower formed by the objective lens, formed by the objective lens. Next, the last is, what is the height of, what is the height of the final image? Final image. What is the height of the final image of the tower? Of the tower. If it is formed at, if it is formed at, if it is formed at 25 centimeter. If it is formed at 25 centimeter. So the same question is extended. We have few more questions here. Here also the given is same. That is, the given focal length of the objective is 140 centimeter and focal length of the eyepiece is 5 centimeter. So first here, what is the separation between the objective lens and the eyepiece? That is, if we consider here, for the telescope we have two lenses. One is focal length of the objective and another one is the lens which we are using towards the eye is the eyepiece. That is objective and the eyepiece. Here the focal length of the objective is greater than focal length of the eyepiece, and also the distance between the objective and to the eyepiece we are taken as length of the telescope. That is L. If you remember the diagram of the telescope, L is the length of the telescope. So L is equals to focal length of the objective plus focal length of the eyepiece. So here the separation between the objective lens and eyepiece. So this is the separation. The distance we call as length of the telescope. So for A, the separation between objective lens and the eyepiece, we are saying as, we are calling that one as length of the telescope. That is L. L is equals to focal length of the objective plus focal length of the eyepiece. We know the value of objective, that is 140, and eyepiece is 5, and the length of the telescope is 145 centimeter. That is the separation between objective and to the eyepiece. That one is the length of the telescope and it is 145 centimeter. So this is the answer for first question. Next, if the telescope is used to be a 100-meter tall tower 3 kilometers away, here the given so here is one tall tower, so its height is 100 meter. So it is viewed from, so it is a distance. At what distance it is? It is at a distance 3 kilometer. Then So if we are observing from here, here is the observer. So from the observer, the height of the tower is 100 meter and it is at a distance of 3 kilometer. Then here the angle is theta. So then theta becomes theta, that is equals to height of the tower one. Height of the tower. So here the height of tower I am taken as h1 divided by the distance from the observer to see the height of the tower, that is distance u, h1 divided by u. So here the given 100 meter, that is for the normal eye for an observer, the height of the tower is 100 meter and it is at a distance of 3 kilometer, that is 3 into kilo means 10 to the power of 3, that is 3 into 10 to the power of 3 meters. Then two zeros, here two zeros cancel, then theta is equals to 1 divided by 30 radians. So at what angle the observer is seeing or viewing this tower is 1 by 30 radians. Next, here what is the height of the image of the tower, that is this height of the tower is seen through the objective. From the objective, here is the object, right? Here is the object. So if we see through this objective, then here one angle is formed, right? That is theta. We don't know the height of the object when we see through this objective. That's why I'm taking this one as h2. So the telescope is at how much distance? That is the what is the height of the image of the tower formed by the telescope? That is objective lens. That is FO. Here the object is at FO. So in the second case, I am taken theta is equals to h2 divided by the distance. Here for the normal eye, I am taken as u. If we weaving through this object, then the distance becomes focal length of the objective, that is h2 divided by f2. We have to calculate this height, that is h2. The focal length of the objective is 140 centimeter. So if we observe these two from the first case, that is waving through the eye and to the objective lens, the angle formed is same, then we can equate these two, that is 1 by 30, that is equals to h2 by 140. Then h2 is equals to 140 divided by 30. So the value of h2 is 3 4s are 12, remaining is 2, that is 2666, that is h2 is 4.67 centimeter. The height of the tower, that is seen through the objective. So this height of the tower is seen only through this objective. That becomes h2 is equals to 4.67 centimeter. The answer for the second option. The height of the tower, that is viewed from the objective lens, that is it becomes 4.67. Next, the last is what is the height of the final image of the tower if it is formed at 25 centimeter, that is least distance of distinct vision, that is d value they given as 25 centimeter. When we get the final image, if we saw through this eyepiece, from this we get the final image, then we have to find the magnifying power of the eyepiece, that is magnifying power of the eyepiece, that is equals to 1 plus Fe divided by D, that is for the telescope ME, that is equals to 1 plus D divided by Fe. Magnifying power for the eyepiece 1 plus the value of the least distance they given 25 and the focal length of the eyepiece they given 5. Then 5 plus 1 is 6. So the magnifying power is 6. The final image of the tower, if we write ME, that is equals to height of the image to the height of the object, then the final image. So this is the final image formed by the eyepiece, that is equals to ME into height of the object, that is height of the tower, that is viewed from this objective, that is HO, that is or H2. So we have the value of ME, that is 6 into height of the objective, that is 4.67. So the final image becomes 6 6 are 36, 6 4 are 12 plus 3, that becomes 6 4 are 24 plus 3, that is 27.6 centimeter. So this one is the final image form, that is viewed from this eyepiece. Okay. In the second case, they asked only the height of the image that is formed by the objective, and in the last case, the final image. When we get the final image, when we saw through the fork, that is from the eyepiece, then only we get the final image. So the final image of the tower is 27.6 centimeter. So in the same question, we find out the 5 values. So this is about the problems on simple telescope. So move on to the next question, that is the problems from reflecting telescope. So they given a Cassegrain telescope, that is reflecting telescope, uses two mirrors as shown figure. Such a telescope is built. Such a telescope is built. Such a telescope is built with the mirrors 20 millimeter apart, 20 millimeter apart. If the radius of curvature, if the radius of curvature of the large mirror, of the large mirror is 220 millimeter, 220 millimeter, and the small mirror, and the small mirror, and the small mirror is 140 millimeter, is 140 millimeter. Where will the final image? Where will the final image? Where will the final image of the object at infinity be? In the last class, we discussed the Cassegrain telescope, that is reflecting telescope. It has two mirrors. One is this one is the objective mirror, and here this mirror they call as secondary mirror. In the question they mention this, the Cassegrain telescope uses two mirrors and they built in such a way that these mirrors are 20 millimeter apart. That is, the distance between the two mirrors is 20 millimeter. So the distance between these two mirrors, the objective mirror and to the secondary mirror or to the small mirror, it is 20 centimeter. That is 20 millimeter. So it is 20 millimeter, and they given the objective mirror focal length. They given focal length of the objective. Sorry, they given the radius of curvature. They given radius of curvature for the objective mirror, that is, or radius of curvature of the objective mirror, it is 220 millimeter, and the radius of curvature for the small mirror, I take an or as, that is 140 millimeter. Then we have to find the final image of the object at infinity b, that is, we have to find out the image distance. We know that focal length is always equals to half of the radius of curvature. From this given data, we can find out the focal length of the objective f4, that is, r value is 220 divided by 2, it becomes 110 millimeter. That is, focal length of the larger mirror is 110 millimeter, and the focal length of the small mirror is, that is, 140 divided by 2, it becomes 70 millimeter. Right? We know the focal length of the objective mirror and the focal length of the secondary mirror. For this mirror, the focal length is 70 millimeter, and for this length, it is 110 millimeter. As the rays coming from infinite falls onto the objective lens after reflecting, they meet or they converge at the point focus. these reflecting rays are focused. This one is objective mirror or concave mirror. As the rays falls onto this mirror, the reflecting rays will meet at the focus. That is, if any parallel beam falls onto this reflecting surface, they meet at the point focus. So this focus, that is the converging point, forms the image of the object. So this image acts as the virtual object for this secondary mirror. That is for the secondary mirror. Then the focus distance of this objective mirror we have 110 centimeter. That is, the image is formed at focus, that is at 1 centimeter, 110 millimeter. Next, this one behaves as the object, virtual object for this secondary mirror. That is, we have to find out the distance u from this secondary mirror. That is, these rays are meeting at this, that is converging at that point. This converging point acts as this one is the converging point for the objective mirror, and this one acts as the image of the objective mirror. Here the focus, the distance, that is from here to here, it is 110 millimeter. That is focal length of the objective. That is, the image is formed at the focus. That's why the image distance from the lens is 110 millimeter. Right. The second one is this image formed by the objective mirror behaves as the virtual object for this secondary mirror. That is, this one behaves as the object for this mirror. Now we have to find out this objective distance, that is u, that is u for the secondary mirror. The distance between these two is the given 20 millimeter, and the image formed is at 110 millimeter. Then we find out u, that is object distance, virtual object for the secondary mirror. U, that is equals to f naught minus this one, the distance between two lenses. We have f naught is 110 minus 20. We get the object distance as 90 millimeter. 90 millimeter. So this one is the object distance u for the secondary mirror, and for the secondary mirror we have the focal length 70 millimeter. So this one is the object distance and this one is the focal length. So by using the mirror formula, by using mirror formula, that is 1 by v plus 1 by u, that is equals to 1 by f. So this one is the virtual object, that is for the convex mirror. So here we have to find out v, that is 1 by v is equals to, if we shift this one to the RHS, it becomes 1 by f minus 1 by u. That is, we know the value of f for smaller mirror. The value of f is 70. That is 1 divided by 70 minus the object distance is 90. So if we take LCM here, so 7 9s are 63. If I take 1 by 10 common, first I take 1 by 10. That is, it becomes 1 by 7 minus 1 by 9. If I take LCM here, is 1 by V is equals to 1 by 70 minus 1 by 90. I will take 1 by 10 as common. 1 by 7 minus 1 by 9. So if I take LCM, it becomes 63. 9 minus 7. 1 by 10 into 9 minus 7 is 2 divided by 63. So 2 ones are 2 5s are. So 1 divided by 5 3s are 15. 5 6 are 30 plus 1 31. That is 1 by V. Then V is equals to 315 millimeter. That is, the image is formed at a distance of 315 millimeter. Right? So here you have to understand, in Cassegrain telescope, the rays which are coming from the object, that is parallel, the rays are parallel and it falls onto the objective mirror. If the rays which are falls to the objective mirror, the image is, that is, the reflected rays are meet at the point, that is, the reflected rays are converged at that point. That point will be taken as image of the object. So the image formed by the objective mirror acts as the virtual object for the second mirror. So for that reason only we have to calculate the object distance for the second mirror. We know the image is formed at focus because the rays are coming from infinite. We know the value of the focal length of the objective mirror. From this objective mirror distance, that is focal length minus separation between these two mirrors, then we get the distance of the object, virtual object, and to the secondary mirror, that is U is equals to 90 millimeter. From mirror formula, we know 1 by V plus 1 by U is equals to 1 by F. Here for convex lens, the focal length is positive and the object is also positive. That's why we know the value of F and U. After substituting and simplifying, we get the image distance that is formed in the Cassegrain telescope is 350 millimeter. So these are the problems based on the telescope topic. So one problem on simple telescope or terrestrial telescope, and this problem is on Cassegrain telescope or reflecting telescope. So one more problem, if we solve on this concept. So an astronomical telescope is in normal adjustment, normal adjustment position, has magnifying power, has magnifying power 5. The distance between the objective and the eyepiece, the distance between the objective and the eyepiece is 120 centimeter. Calculate the focal length of calculate the focal length of objective and the eyepiece. So in the question they have given one astronomical telescope. So for this telescope we have two lenses. One is objective, that is placed near object, and another one is eyepiece, that is placed near the eye. So this one is the objective and this one is the eyepiece. Next, they given for normal adjustment the magnifying power is 5. They given m value is equals to 5, and then they also given the distance between the objective and to the eyepiece, that is 120 centimeter. That is the length of the telescope. They given L is equals to 120 centimeter. Next, calculate the focal length of the objective and eyepiece. We have to calculate the focal length of objective, that is FO, and we have to calculate focal length of the eyepiece, that is FE. So they given only the magnifying power and the length of the telescope. We know that the length of the telescope L is equals to FO plus FE. We have only these two relations. They are given. We have to find out FO and FE. So magnifying power, the formula for magnifying power is for the telescope, that is FO divided by FE. By using the formula of magnifying power of the telescope, m is equals to FO by FE. So they given the value of m is 5. 5 is equals to FO divided by FE. So FO is equals to 5 FE. So taken this one as equation 1. Now substitute this one to the length of the telescope L. The value of FO they given 5. Once again I will write here FO plus FE. The value of FO is 5 FE plus FE. The value for L they given is 120 centimeter. 120, here it is 120 centimeter. So 120 is equals to 5 Fe plus Fe is 6 Fe. Then Fe, that is focal length of the eyepiece, that is equals to 120 divided by 6. That is 620 centimeters. 6 2s are 12. That is 620 are 120. So Fe is equals to 20 centimeter. That is the focal length of the eyepiece. So now substitute the value of Fe into the equation 1. We get focal length of the objective. 5 into the value of Fe is 20. Then F of the object is 5 2s are 10. That is 100 centimeter. So this is the focal length of the objective and this one is the focal length of the eyepiece. So here, observe here 120. So FO is always greater than FE. By this, we completed the chapter ray optics. So in the next class, we will solve few problems which they asked in the previous examination. If any doubts, then ask me in the group. I will clarify in the next class. So this is about the chapter ray optics. By this, we are completing the first chapter of the second part, that is ray optics. From this chapter, we are getting 9 marks. So one question from 1 mark, and one question from 3 marks, and one question from 5 marks. In 5 marks, they may ask problem or they may ask the derivation. So you have to practice. In this chapter, hardly we have 4 to 5 derivations for 5 marks, and we have to solve the problems on lenses, mirrors and prisms. So in the next class we will discuss few problems which they asked in the previous examination. Thank you.